Hi, everyone, and thank you for joining today's webinar from ATA Engineering. We're going to take a look at the LiftShip program and specifically an exciting set of new tools that ATA is developing with the Femap API to automate the simulation of ship module lifts and turns with Femap. My name is Jonathan Hill. I'm a business development engineer here in ATA's Northern Virginia office, right outside Washington, D.C. And I'm really excited to be joined by my colleague, Vicki Harris, who is also here in the Northern Virginia area with me. Before we get started, I do have a couple quick slides just to give a top-level overview of ATA in case you're unfamiliar with us, and then we'll turn it over to Vicki. ATA is well known for providing high-value engineering services where we have expertise with test and analysis-driven design. We're really passionate about helping our customers overcome their most difficult product design challenges. Those are usually multidisciplinary, and we work with a lot of different industries, just some of which are shown here. We're also able to leverage that experience and expertise with the software that we get through these projects through our role as a Siemens partner and value-added reseller. In that capacity, we offer training, free resources, and hotline support for a wide variety of Siemens products. Some of those are shown here. That includes SimCenter Femap, which we'll be focusing on today, but other powerful tools as well, like Nastran, NX and SimCenter 3D, Star CCM+, HEEDS, AIMSIM, and more. We have a technical support hotline that runs from the beginning of the day on the East Coast until the end of the day on the West Coast. And that's staffed by our project engineers like Vicki, folks that are using the tools every day, know them inside and out, probably already have it open on their screen when you call in. And we also develop the official SimCenter Nastran training materials and our Siemens preferred provider of training in North America. So that means that if you go to Siemens and you request, for instance, a dynamic analysis Nastran class, Siemens is going to point you to a class that was developed and is taught by ATA instructors. Siemens has also recognized ATA as a smart expert partner with validated expertise in Femap, Star CCM+, and SimCenter 3D. I also invite you to check out our website after today's presentation. There's a lot of great content up there, from product information, a calendar of upcoming events. You can reach out to our hotline through the website. But my favorite part is always the free resources. There are a ton of really great resources out there, free APIs and macros, white papers, on-demand webinars, you name it, it's probably up there. And if it isn't, we would love to hear from you. So all of the content up there is developed by our engineers for folks like you. And so that's kind of my final plug, is if you have ideas for a new API you'd like to see or a new webinar topic or anything, please reach out and let us know. We'll have our contact info at the very end, and we would be happy to discuss that with you and potentially add it to our upcoming list of content to develop. With that, though, I'm really excited to turn it over to Vicki. Vicki, it's all yours.
All right. Thank you, Jonathan. As Jonathan said, I'm here today to talk about LiftShip, purpose of which is simulating ship module lifts and turns with Femap. So I'm going to start out by telling you about the NSRP LiftShip program. Then I'll talk about the tools we've actually been developing for LiftShip. I'll start out by telling you about the workflow that goes into simulating lift and turn. Then I'll give you a little bit of information about the Femap API, which is what we're using to build all of these tools. And I'll finish up by showing you the two primary tools that we've been developing for this effort, the model generator and the lift and turn tool. All right, LiftShip is a program funded by the NSRP, which is the National Shipbuilding Research Program. NSRP is interested in lifts and turns because it's a very important part of the shipbuilding process. For those of you who aren't familiar, when large ships are built, they're typically built in sections or sort of slices of ship. And when each section is complete, it's then lifted and sometimes rotated into place within the larger ship structure, and then the assembly is completed. As you can imagine, these ship sections can be quite massive, and I mean that literally, like we're talking thousands of tons here. So there's a significant amount of force and stress going on during these lifts. And as you can see from the headline shown here, if something goes wrong, the results can be catastrophic, as terrible as shipyard workers dying. But even short of that, if you've got something like this where your crane is falling over, that's going to do significant damage to the shipyard, to the ship itself, to the lifting equipment. And that's going to cost the shipyard a significant amount of time and time and money. Why do these failures typically occur? It could be because the equipment itself is damaged or overloaded due to miscalculations. It could be environmental. Maybe there's some wind or rain that wasn't expected, or perhaps snow or ice has been building up on the ship section, which makes it heavier than anticipated. Or it could be calculation issues. The shipyards generally do analysis ahead of time to figure out how the lift is going to go. But sometimes those calculations could be erroneous due to assumptions that aren't valid, or using data that's out of date, or perhaps changes made to the ship section after those calculations are performed. The way that these calculations are typically performed, it could be as simple as pencil and paper calculations, probably with a calculator. It could be something a little bit more complex where you've got spreadsheets set up to do it, or it could be as complex as using finite element analysis software. FEA, as I'm sure all of you know if you've been using Femap, offers highly detailed insights into structural integrity. Simulating something like a lift in Femap is going to tell you about local yielding, any distortion or buckling that's going on, and the need for support structure to be added before you do the lift. So if FEA is so great, why isn't it being used more? Well, the problem is that this FEA software requires a level of expertise to efficiently develop models that yield accurate results. For shipbuilding, these sections for large ships, the models that are required to accurately represent them are pretty detailed and complex. So building that in Femap, even if you are an expert, can be quite tedious. The legacy hand calculations on the other side are much faster, and you can often mitigate the risk of large-scale failure as long as you add in enough conservatism. So the benefits of these legacy hand calculations, which are speed and simplicity, outweigh the potential of FEA to identify these problems like local yielding and need for support structure, which you could get by using FEA. So the LiftShip program's driving goal is, what if we can tip this balance and achieve the accuracy benefits of FEA in less time by automating the FEA simulation process as much as possible? There have been 2 stages of LiftShip so far. In LiftShip 1, we automated the translation of geometry from ShipConstructor CAD software to Femap FEA software. I'll be talking more about the actual translation process later on, but ShipConstructor is a sort of ship design software that a lot of the shipyards use. It's great for laying out ship architecture. It's got lots of ship specific stuff in there, like defining equipment, HVAC systems, all that stuff. It's great for ship design, but of course it doesn't have anything built in for this kind of FEA. So we needed a way to bring that data into Femap as quickly as possible. So we developed a tool for that that we call our model generator during LiftShip 1. In LiftShip 2, which is ongoing right now, we've been focusing on the simulation of the actual lift and turn. So we've been trying to automate the process of setting up that analysis as much as possible. We've also been adding some enhancements to the geometry translator and some tools for visual reporting. All right, so that's the LiftShip program. ATA's efforts within that LiftShip program have led, as I've said, to the development of 2 major tools. We see the lift and turn analysis procedure as basically having these 5 to 7 steps. The first step is to translate your geometry from ShipConstructor to Femap using our model generator tool. Next, you'd mesh the ship module, and then you define the lift steps using the lift and turn tool. Once you've used the lift and turn tool, you're ready to just hit the solve button and have Nastran analyze the lift process. And then you'd review the results and determine, based on the loads and the stresses you see in your results, whether or not you need to add any support structure to the ship. If so, then you can just analyze the lifting solution again once you've added that structure and check that that support has resolved the issues. If you've got positive margins at that point, you're ready to do your lift. So the 2 major tools that I'm going to show you in a minute, the model generator and the lift and turn tool, are both built on the Femap API. The API is also known as the Application Program Interface. Technically, it refers to the language and libraries that you can use to control Femap, but it is also used to refer to individual API programs. So, I might say, oh, I wrote an API that changes the background color. These work by basically automating the tasks that you would otherwise do by opening Femap and clicking on things or entering data manually. And it can run from inside Femap or from outside through another program like Excel. The native language for the API is Visual Basic, but there are other languages that can be used like Python or C#. Most of the tools we've written for LiftShip are in Python. It's pretty easy to do that conversion. And the benefit of that is means you can bring in all kinds of outside libraries to help out. And so you can end up building something quite complex on the Femap API. And the API contains virtually every command in Femap. So if there's a button you can click in Femap or a menu option in Femap, you should be able to find that in the API. Basically, the idea is you're automating repetitive or tedious tasks here. I will say I have used APIs from a few different software programs, and I found the Femap API to be by far the easiest to use and most sort of commonsensical. So I've got a few pictures on the right-hand side of the screen here. If you've ever used the custom tools menu in Femap, you've got all of these folders of different programs in here. All of the programs within these folders are APIs. And you can also access them by going to your Femap installation and clicking on the API folder. You can see all of the same folders are set up here, and you can actually look at the source code of these commands. That's really helpful if you're looking to get started with your own API. You can start looking through these codes. You can generally find one that sort of does, does something similar to what you're looking for. Like if you're looking to do something to the background, you can come through to views and look at the change background color script. And it's a great way to get started figuring out how to use the API. There's also plenty of documentation for it in the regular Femap help. You may be familiar with this window. I know it's a bit of an eye chart, but underneath, commands, user guides, and examples, there's an option for the API, and all the commands are documented in there. It'll tell you what the inputs should be, what the outputs should be, what the format should be. It's a great set of documentation. It's really helpful. So that's the API. Now I'll show you some of the stuff we built with it. The first tool that I want to show you is the Femap model generator. The way that I said before that the first step of this process is to bring in the ship structure from ShipConstructor into Femap. The sort of default way to do this, which I'm sure you're all familiar with if you've ever had to import CAD into Femap, is you'd go to ShipConstructor, you'd write out a bunch of step files or IGES or whatever you prefer, and then you'd re-import those in Femap. And then once you had all that solid geometry in there, you'd then have to mid-surface all of those parts to get 2D surfaces that you could put a 2D mesh on. Because of the size of these ship sections, even the export and import step can be quite time consuming. And then of course the mid-surfacing, if you've ever done mid-surfacing, you'll know that that can also take quite a while, because first you have to mid-surface and then you have to make sure all the parts intersect with each other and extend surfaces. And that's generally the part of geometry preparation that takes the longest. So what the model generator does is, instead of using that external file, the step file, instead we query the ShipConstructor database directly. We can access the ShipConstructor database, and we can look at, say, a plate, and we can see the actual geometry definition of sort of the underlying 2D plane that defines this plate. So we can pull all that point and edge information into Femap, and then we can use the API to create that plate from scratch as a 2D surface. And then we just repeat that process over and over again for all of the parts in the ShipConstructor database. And then still within the API, we can do all of the surface intersection that's necessary. We attempt to extend surfaces where possible. We can also automatically assign entity names and physical and material properties, which eliminates the time needed to set that stuff up manually. So you end up saving a significant amount of time, and you basically get 90% of the way to being ready to mesh your model in about 4 minutes for the example I'm showing here. Some of the other features we have on the geometry translator are the user can select the geometry level of detail, and we're now also executing all of this through a graphical user interface, or GUI. So I'll show you real quick what I mean by level of detail, and then we'll jump into Femap. This is an example of a ship model that's very kindly provided by the guys at ShipConstructor. This is the same model twice, but in one of them, I've included all of the detail. So in this one, you can see I've got some stiffener cutouts, I've got penetrations, I've got corner treatments, all that good stuff. And in the other model, I've just switched all that off. So it's exactly the same thing, but minus all of the detail. Whether you include those things or not is kind of up to the analyst. It really depends on what sort of analysis you're doing and how big your model is and all of that. So we'll left that up to you. All right, so the graphical user interface, I'm going to jump into Femap to show you that. Let's see. So this is what our graphical user interface looks like. I mean, it's not by itself all that interesting. It's pretty straightforward. At the top here, you put in some information about where your ShipConstructor model is and how to access the database. Down here, you tell it where you want the Femap model to end up, and then you can, select whatever detail you'd like to include or exclude here. And you hit the translate button. I'm not going to do that right now because it does take a few minutes, but after about 4 minutes for this model, you have a nice Femap model to open. So this is what it looks like fresh out of the geometry translator. If I zoom in a little bit, you can see this is already 2D surfaces. For the most part, things are connected up and ready to go, but any kind of automated process like this, it's never going to get you 100% of the way there. I said before, this kind of gets you about 90% of the way to meshing. And then we set up some stuff to help you fix the rest of it. So for instance, here, we're showing some what we call orphan surfaces. This is basically us saying, we're pretty sure this is supposed to be connected to something, but it isn't. So you should look at this and fix it. So in this example, if I zoom in, you can see this gusset really should be coplanar with this stiffener. And these other two stiffeners right here did manage to become coplanar. But this one got missed by our filters. So you might want to come in here and say, modify, move by solid. And then I think if I just do, see. If I just move along a vector, I can come along here in the -y direction. That should move us into place, yeah. So it's just that kind of correction that you may need to do. Femap also has some really nice tools for doing that kind of stuff. My new favorite tool is the Mesh Control Explorer, which I think is new as of 2021, either 0.1 or 0.2. This is basically a toolbox that is geared entirely towards this problem, which is I've got this big model, most of it is connected up, but I need you to tell me, I need you to tell me what else needs to get fixed before I can mesh this. So there's a lot of tools in here. The ones I want to highlight are the edge tools. So this first tool will show us edges paired by mapping and proximity. This is basically Femap saying, I found these edges next to each other and I have mapped them together. And when I say map them together, that basically means when you mesh this, nodes are going to be shared along these edges. So looking at this, it makes sense. I've got two plates here and they've highlighted the edges between them saying, these two plates are sharing edges here. That's great. That's exactly what I want. So this is basically the tool that's like, this is all the stuff that already works. The next tool along is the, let's see, unpaired free edges that are not adjacent to other edges. This one is basically saying, these are all the edges I don't think are connected to anything. Some of these make sense. This edge right here is unpaired and it should be unpaired. Some of them though, I don't like. Like these stiffeners that come out through here. I think the top edge should be unpaired, but I think this bottom edge should be connected to this plate. So that's something I need to remember for later. I'll show you a quick way to fix that in a minute. The next one along is show unpaired free edges that are adjacent to other edges. This is telling me, this is Femap telling me, these are all the edges I found that are next to each other, and I think they should be paired, but they aren't right now for whatever reason. So I can come through here and check these out one at a time. For instance, this one here basically looks like it's found that these two plates are next to each other, but they're not officially paired yet. Do you want to pair them? So I can come in here and say imprint points, which is basically saying, yes, please pair them. And that takes care of it. You can also come in here once you've explored this data a little bit and say imprint points all, and it will attempt to do the imprint points for all of the edges it found. That takes a couple of minutes, so I won't do it on this model. So that saves you a lot of time. And then the one additional tool I will show you is show edges that are adjacent to surfaces with no imprinted edge, which is basically the same thing as the last tool, but instead of finding two edges that are unpaired, it's going to find an edge that's next to a surface that doesn't have an imprinted edge, thus nothing can be paired. So the stiffener I found down here that wasn't connected to the plate, this tool should find that location. And you see it takes a little bit of time, but it'll get there soon enough. And this is going to have a similar feature to the unpaired edges, where I can right click and say fix this one case, or I can right click and say fix all of them. So once this completes, it'll highlight all of the faces and edges, which is because it's highlighting faces, it's a little bit hard to see. As you see, a lot of stuff is lit up here, so it's somewhat easier to come through by pair. Let's see, this one, you can see I've got this face over here, has found some of these stiffener edges inside the structure. It thinks that these two, this curve and this face, should be paired, and they aren't right now. So as I said, I can come in here and say imprint edges or imprint edges all, take care of the whole thing. So that is going to speed up the sort of the remaining 10% of this process for you quite a bit. Your other options for doing this sort of thing are generally found under geometry, mid-surface. You've got things like trim with curve. If you have a surface that sort of extends past where it should go, that's where you might use trim to solid or trim with curve. And you've also got an extend option here for if a surface doesn't reach as far as you think it should, like it stops short of the bulkhead it's supposed to be attached to, you'd use the extend tool to take care of that. And then you've got some options like intersect to make sure you've got, if you've got two surfaces that overlap each other, if you want to use intersect, you can kind of imprint them on each other so that essentially they'll be sharing edges when you mesh it. So that's pretty much it for the geometry preparation. While we're here, I'll just show you real quick how the model generator has put in the name of the parts. So these are all the names of parts out of ShipConstructor. Makes it easier if you're looking for a specific part to come in here and highlight where that part might be. And we've also got the material definitions in here, and also all of our properties. And it's you can see we've grouped everything by a single property here, rather than having a single property for every part. So it's easy to figure out, which parts share properties. All right, so that is the geometry preparation stage. Let's go back into PowerPoint real quick. Now I want to show you the lift and turn tool. This tool, the idea behind this tool is that someone who knows how to design a lift is going to come in here and be able to tell our tool how they think the lift should be designed. And then we translate that with our tool into Femap speak, as it were. So to demonstrate this, I have designed a lift of my own. I am very much not a lift and turn analyst. So if any of you are on the phone, please excuse this lift. It's definitely not the most efficient way of doing this, but it does highlight, I think, some important features of our tool. So this is our ship section. It's kindly provided again by the guys at ShipConstructor. I have started out this lift by attaching a chain to a lug on the hull right here. And I've also got a couple of lugs on what is currently the underside of the ship section. And I'm running chains from those lugs up around this corner and vertical from there. And I've put a couple of chafing guards in here to protect the corner there. Like I said, this is probably not the best way to lift this, but this is how I chose to do it for the demonstration. So once we've lifted the structure, we can start turning it by raising the chains on one side and lowering the chain on the other side. Eventually we'll reach the vertical configuration, and you'll see at this point our chains are not vertical anymore because we had to move the crane heads apart as they can only get so close together when you're doing this. So at some point the chains are going to be non-vertical, and that's something our tool can handle. Then we can detach this one chain here and have it in a free hanging configuration, and our tool in fact can calculate the position in which it will be hanging when it's free hanging, assuming you just have one set of lugs that are collinear with each other. From the free hanging stage, we'll attach new chains to the roof here and start lifting on one side and lowering the other again until we reach this upright component. So I will take us back into Femap now to show you how the tool works. So this is my ship section Femap model. I've already meshed this, but I turned off element borders because it's kind of busy otherwise. I have modeled our lifting lugs with RB2 rigid spider elements. If you wanted to model these with the 2D or 3D mesh, you could do that too. But we used RB2s because generally when you're lifting, the lugs and the chains and the cranes are going to have, typically they're going to have load ratings rather than stress allowables. So all you really need at this location is the amount of load going through the lug. But like I said, if you want to put in a proper mesh in there, you can do that too. So I've got a lug over here, I've got two on the underside, And then I've got 2 on the roof for that final couple of lifting stages. And I've also got some chafing guards here and here, and 1 on the hull. So once I have all this set up, I'm ready to go into the lift and turn tool. So this is the lift and turn tool. This again is built on the Femap. Let's see if I can organize my windows a little bit better here. This is built on the Femap API. Like I said, we have used a Python library on top of that to get this very complex GUI, but basically every button you press in here is eventually going to take you back into Femap. So to demonstrate, when you're setting up a lift, the first thing you have to do is define your rotation axis. About which vector are you going to be rotating this model? So if I hit select vector from model, it brings up the familiar Femap vector definition dialog. So I'm going to be rotating this about the x-axis. So I just hit OK here. Next, I want to define each of my lift steps. I'm not going to define the entire lift that I showed you before. I'll just show you kind of what this starts to look like. So I'm going to call my first step the pick step. I'm going to select a gravity vector for it, again, using the usual vector dialog box. This time it's going to be +z. And then I start adding cables or chains or whatever you want to call them. So this is, again, just going to bring me back to a Femap dialog to select nodes. That's not what I want. If I want to add chafing guards, shoot, it's gone behind it. If I want to add chafing guards, I can select that here, which again is just picking nodes. And if I want to select a crane head position that's other than vertical from the last rigging point, I can also do that in here too. Like I said, I'm not going to show you the whole process. We do have an option for saving a defined lift to a text file. And that is what I've done here. So here is that 6-step lift I showed you on the PowerPoint slides. If I expand this out, you can see all of the stuff I've defined. I've got gravity vector. I've got 3 chains. Each of these chains have a pad I defined, and some of them also have chafing guards. For my free hanging case, I have a gravity vector that was calculated for me by this tool. And also I think on some of these, this one, I've got those non-vertical crane heads. So if you can see those. Yeah, I've got a vector defined here. So once I've got all this all set up, I can hit generate load cases, and that will take us back into Femap, where I now have all of my loads and boundary conditions set up, but not in this model. Let's see. All right, so here are my loads and constraints for this. This is all done again by the Femap API based on the definitions we put into our GUI. So I've got a gravity vector defined for each of the lifting steps. I've got constraints defined for each of the lifting steps. I have a simulation. I've got an analysis ready to go. I can just right click and hit solve or analyze whenever I'm ready. And I also have some groups that show me the additional stuff that got created with the lift and turn tool. For each step in the lift and turn, or let me back up a second. If you are looking to rotate a finite element model or to simulate a rotation, there's basically 2 ways you can do it. The first is you could rotate the model itself, the nodes and elements, just physically rotate them for each step. The downside to that is either you lose the model configuration every time you rotate, or you could save each configuration as a separate Femap model. But then if you need to make design changes, like if you want to add support structure, you're going to have to do that 6 times, once for each model that represents each load step. So rather than changing the model itself, we're changing sort of the reference frame. This is why we have a different gravity vector for each step. And that's also why if I flip through these groups and highlight what's in them, you can see these coordinate systems that are changing position for each step. For our for the simple lug locations where it's just a lifting lug and it's going vertically to the crane head, we just use a constraint to represent that. If we have to put in chafing guards, where it goes around a corner like this, on those cases, we are including rod elements to represent the intermediate steps of the chain. And then we have basically coordinate systems and springs set up so that the force in the rod here is always going to be equal to the force of the constraint going to the crane head. We've also got some other Nastran magic in here to make sure that the loads all balance each other, but still give you the correct answer. So generally, you might want to poke through these groups to make sure this is doing what you think it's going to do. The other tool that we have available to you is a tool to actually animate your lift. This is all, I'm doing it through a command right now, but it will be eventually part of the custom tools menu. So this is just rotating through all of the gravity vectors that I've defined, just so I can kind of eyeball it and make sure this is behaving the way I expect. Generally, yes, this looks correct to me. This again is a tool written with the Femap API. All we're doing here is just taking, there's a lot of different ways you can define a view orientation in the Femap API. So we're just using one of those and interpolating between various vectors and refreshing the view each time. And it comes out to this nice animation. We actually have to wait for this to finish before we can solve. But as I said, the analysis is ready to go whenever you are. So you can right click on that and say analyze, and this model takes about 5 minutes to solve. Once you've done that, then you're ready to look at each load step and make sure you don't have any negative margins. So I have a bunch of views set up that come out of our lift and turn tool. This is another nice feature you can do. Because you are going to get a lot of data out of this, we set up a bunch of views to let you kind of step through them all individually quickly. So the first thing I want to look at is the forces in my lifting chains. So this is showing me just the forces in the 3 lifting chains for the first step. I can take a look at these loads and compare them to the load ratings on my chains and my lugs and my cranes, make sure I'm within allowables. And then I can just start stepping through the other load cases. We're going to reorient to the appropriate gravity vector each time. And here's our final step. So that's pretty straightforward. The other thing we want to look at is stress in each of our sections. I'm not going to show you every step because most of them are pretty straightforward. They're all below margins. I have set up my stress plot here so that the top of my color bar is at my allowable. I'm using 40 MPa here, which is kind of low for steel, but go with it for now. Anything in red then is overstressed. So like I said, the first 5 steps are pretty boring to look at. They're all much below the allowable, and so we don't need to worry about them. The 6th step, which you have already seen, does have a negative margin. The margin makes sense. We have a lifting lug right here. There's a lot of load going through this. That load is then ending up on this roof stiffener here. And then it's trying to get into this wall stiffener, this vertical stiffener right here. And there's a gusset plate that connects them. But if I zoom in a little bit more, you can see this gusset plate doesn't fill the whole width of this roof stiffener. So there's a little bit of a stress concentration here. If I switch back to Femap, you can see this a little bit better. So here's the geometry as it looks in ShipConstructor. So you can see that that plate doesn't cover the entire length of this roof stiffener. Now, for solving this problem, generally the shipyards are looking for the quickest, simplest solution possible. So in my mind, the simplest solution here is to just take another plate and weld it to the other side of these stiffeners, the opposite side to where this current gusset plate is. And I'm going to make it bigger than the current gusset plate so it fills this entire width. And then once I get into Femap, I can also play with what I think the appropriate thickness should be and that kind of thing. So if I go to my fixed model, you can see that I've already gone ahead and done it. I've created a new property to make it easier to pick this out. I just called it new plate. Now you might be looking at this plate and thinking, why is it kind of wobbly around the edges here? Well, that's because I did this just the quickest way I could think of, which was just copying the elements on this existing gusset plate, copying a few more on this stiffener, and then a bunch more on this stiffener to give me the sort of general outline of where I wanted to add new material. And then I drew in a few elements here. And then once I've done all of that, I can use the coincident nodes tool, which is under tools, check, coincident nodes, to merge all of the nodes together on my new plate, and also to then connect that plate to the rest of the model by merging nodes only around the boundary of this plate. The reason I only do it around the boundary is because in reality, this is going to get welded to the existing part. And if we merged all of the nodes across the entire area of this, it'd be more akin to gluing it, which is not what's happening. So I've put in what I think, I've put in the support structure I think that we need here. We didn't significantly change the CG of this model. We haven't changed anything about the lifting setup itself, like all the lugs and the chains are in the same places. So I can just go back down here and analyze the same setup. Another 5 minutes and I can look at the results. And I will skip to the conclusion for this. Here is that stress in the final lifting case. You can see I still have my color bar set to my allowable. You kind of can't see it actually. There we go. You can see it's still set to 40 MPa. So anything that's red is overstressed. But if I look in here, I've got lots of nice greens and things. So it looks like this has solved my problem. If I just look real quick for the next highest stress, it's over here. I can see that because it's I've got the max stress label on there. That's coming in at like 33 MPa. So that's also comfortably below the allowable. So this lift is ready to go. All right, so that is the lift and turn tool. Like I said, there's a lot more to it, but for the sake of time, I won't go into it now. If anyone wants to ask questions about it at the end, I'm happy to answer those. In the meantime, to wrap up, we wanted to do a quantitative cost analysis of this. So, you know, all these tools are well and good, but what does it actually mean to the analyst? So to determine this, we thought about how many hours we think it would take the average ATA engineer. As Jonathan said at the beginning, we do engineering services is our whole thing. So, you know, estimating level of effort for this kind of task is something that we do a lot. My estimate for this is that it would probably be about 40 to 48 hours worth of effort if we don't use the LiftShip tools. There's a lot of geometry preparation that we'd have to do, and also the setting up of the loads and constraints would be quite time consuming. By leveraging the tools we developed under this program, we estimate you could probably get it done in, you know, maybe 20 to 24 hours. So about 50% savings in time and effort, which is pretty significant. It does take some time to become comfortable with the tools, but once you get the hang of them, you know, you're really rolling in the geometry preparation and the loads and constraints setup. So just to summarize, LiftShip is an NSRP program for automating the simulation of ship module lifts and turns. If you're interested in learning more about NSRP or about LiftShip, you can go to the NSRP website. And especially if you're an NSRP member, you may be able to learn even more. ATA engineering as part of LiftShip is using the Femap API to produce a suite of LiftShip tools. The primary tools among those being the model generator, which automates the ShipConstructor to Femap translation, and lift and turn, which automates the setup of the lift and turn analysis. And the combined use of these tools with practice should result in significant time savings for the analyst. All right, that's all I have for today. Are there any questions?
Awesome. Thank you so much. That was really cool to see, and, you know, really cool to think about how much easier it is to do these analyses now, and hopefully allows FEA to be used more widely. Be happy to take any questions. You can either submit those through the chat or through the Q&A tab. While we're waiting for some of those questions to come in, perhaps I'll mention that if you are interested just in general more about the Femap API, we've actually done past webinars introducing the Femap API and how to get started and resources that are available. And so if you search on our website or our YouTube page, you might be able to find those on-demand webinars as well. Looking for any questions, you can certainly, maybe I'll steal the screen share back and just get our contact info up there. But yeah, certainly welcome any questions now. You can also reach out to us after the presentation, and we'd be happy to follow up with you then as well. Very good. Well, I don't see any questions coming in. Again, please feel free to reach out to us this afternoon or in the future if you come up with anything else. We're going to record this, and I'll send the link to that recording out when it's available. So keep an eye out for that. And otherwise, it was great to have you all here, and everyone have a great afternoon. Thanks.
Thanks, everyone.